Hopefully the technology is going to be working again. What we're going to be doing today is we're going to be doing independence. Okay? Can somebody just tell me informally what does it mean for two events to be independent? Yes? Knowing the outcome of one event does not affect the outcome of the other. So we talked about conditional probability, the probability of A given B, right? This was equal to what? The probability of A intersect B divided by the probability of B. This was our formula for conditional probability. If A and B are independent, what should this equal? Yeah, it should just be the probability of A if independent. You know, if knowing B happens, you got to move because you're blocking the camera. If knowing B happens gives you no information about A, then the conditional probability of A happening given that B happening is the same as the probability of A. We've gotten no additional information from learning that B happened. This is not a good definition. And the reason it's not a good definition is we have a division by the probability of B going on here. And so whenever you divide by any number, you always have to check and make sure, is this 0? You know, do I have 0 over 0? Do I have infinity over infinity? Well, with probabilities, I don't have to worry about infinity over infinity, but I do have to worry about 0 over 0. And so we talked about how a nice way of writing this is the probability of A and B is the probability of A given B times the probability of B. Well, if I multiply through by the probability of B, this becomes the probability of A, probability of B. And this becomes a really nice definition for independence. A and B are independent if the probability of A and B both happening is the probability of A, the probability of B. And we often call this the multiplication rule for hopefully obvious reasons. So basically the probability that they both happen is the product of their probabilities. Okay, and if we have more and more events, you might expect to be able to iterate this. And so if we have the probability of A and B and C, if they're independent, what should that be? So A, B, C independent, what should the probability of A intersect B intersect C equal? The product of their probabilities. The probability of A, probability of B, probability of C. If A is independent of B and A is independent of C, should A be independent of B and C? So if A doesn't depend on B and A doesn't depend on C, it shouldn't depend on A and C. If you're willing to accept this, you can prove this by grouping. I call that one event first. And then by grouping, we would get the probability of A intersect B intersect C is the probability of A, probability of B intersect C. And now we use this again, probability of A, probability of B, probability of C. But this assumes A is independent of B and C, which is, not an unreasonable assumption. This part over here is no problem. If A, B, and C are independent, the product of their probabilities is the probability that they all happen. The question is, what about the reverse direction? If we know that this is true, are the events independent? So does it go both ways?
I think yes, because multiplication is commutative.
So multiplication is commutative. So in terms of whether or not this formula is true or whether or not the events themselves are independent. For instance, what if event C happens with probability 0? Then I could have A and B being dependent on each other. Maybe A equals B. And so just because this multiplication formula holds does not mean the events are independent. So unfortunately, the notion of what does it mean for things to be independent is a lot more complicated. It's not enough to just check this condition. So if we want events to be independent, if we want 3 events A, B, and C to be independent, we want this multiplication formula to hold. what else do we want to hold? Let me see if we can put down here. Okay, so A, B, C independent. We want the probability of A intersect B intersect C is the probability of A, probability of B, probability of C. What else would we want? So in addition to, yes?
You want the group, so A intersect B, independent of B intersect C.
Good, so we want to do it everything now in pairs. The probability of A intersect B, probability A, probability B, probability of A intersect C is the probability of A, probability of C, and then the last is the probability of B intersect C is the probability of B, probability of C. We need all of these to be true for independence. If all true, then A, B, C are independent. And then if we had 4 events, what would happen is for 4 events to be independent, the probability of the product of all 4 is the product, the probability of the intersection of all 4 is the product of the probabilities. The probability of the intersection of any 3 is the product of the probabilities. The intersection of any 2 is the product of the probabilities. I'm not going to bother with just one thing floating because that's not so bad. And then I'll leave it to you as an exercise as to how many cases do you need to check the more events you have. If you have 12 events, how many conditions would you have to technically check? Okay? Now, a lot of times, we don't have to actually go through the analysis. If event A is tossing a fair coin and event B is rolling a die, and event C is the weather in Hawaii, those events are probably independent, and I probably don't have to go through the calculation. Okay? So I'm not going to say too much more about all of this. It's a nice example to try to come up with events A, B, and C such that any 2 of them are independent, but the 3 of them are not. And so basically, you want a situation where somehow if you know 2 of them, that forces maybe the value of the 3rd. Going back to die, these are really good examples of looking at sums of die rolls. All right, so I'll leave that as something for you to play with. Okay, any questions on independence? Okay, so this figures out how to calculate the probability of a lot of intersections. And if I want to calculate the probabilities of the intersections, I can do it if the events are independent in terms of stuff like this. All right. So what I want to talk about now is some applications of calculating probabilities of events. So let's do inclusion-exclusion. So this is going to the derangements. So one of the big examples is, one of the big questions you should always ask is who cares? For the most part, I really don't care about taking n people and randomly shuffling them down and putting them back in class. Okay? I'm probably not going to just randomly hand back exams and just whoever's exam you get, that's the grade you get. We're not going to really do stuff like this. Why might we care about stuff like derangements? So there's a couple of applications. One application is in graph theory. So application. And again, I don't want to go into too much detail now. If anybody's interested, I'm happy to do more. I just want to give you a little bit of a sense of why we give a damn. Okay? What do you think you're trying to do when you build a computer network? And you have a bunch of computers that you want to be able to communicate with each other. What do you think your goal is? Maybe fastest average distance. That's one of many applications, one of many things you care about. Big thing is you want maybe every computer to talk to every computer. I know a really easy way to do that. How can I make sure every computer talks to every computer?
Put a little node in the center.
Okay, I could do this, but this is an extremely dangerous way to do it. So if I do this, yes, every node can talk to every node. This is the Panama Canal model. This is the Suez Canal model. What happens if you have failure here? I'm sorry? It's disastrous, right? A failure here means now nothing can talk to anything. You have such a critical point that a failure here spells the end for your system. If you think about what happens if the Panama Canal closes, ships have to now go all the way around South America. If the Suez Canal fails, they have to go all the way around Africa. So when you have a system like this with 1 or 2 key strategic points, this is very bad. There's a simple way, though, to make sure that every computer can communicate with every computer.
Draw lines from every computer.
Yes. And this is the model that got us things like Williams in New York, when we didn't really worry about prices of things, and we just draw everything, and we don't worry at all about how much this is costing us. This is why your tuition is so high. All right. So we have something like this. We have the complete graph. This will work. Everybody will communicate with everybody. If one node goes down, not a big deal. We have a lot of redundancy, but it's very expensive. A huge area of research is devoted to trying to construct graph networks where you have a small number of edges. You want the number of edges to grow linearly with the number of vertices, and you still have fast connective times on average, and you don't have any strategic points whose failure will cause trouble. And so it turns out a lot of this comes down to what's called random graph theory. And essentially, it's strange, but one of the best ways to construct these graphs is to just randomly connect edges. And most of the time, it will work well. And we can even prove how well it works. Sometimes we do what's called bipartite connections. We have the left and the right. You can't be connected to anything on your side, but you can be connected to things on the other side. And so here, each vertex is connected to one and only one thing on the other side. And then what I might want to do is, if I have something like this, can everybody talk to everybody? No, in fact, you can only talk to one person. What you then do is you do a couple of connections like this. Is maybe each vertex is connected to 3 things or 4 things on the other side. What does that correspond to doing? It corresponds to, I have numbers 1 through n here. I have the numbers 1 through n here. I reshuffle them. And I just want to make sure I never do the same thing again. I'm talking about a random permutation, and I want to avoid derangements. I want to avoid situations where, I'm sorry, is a derangement where you have somebody aligned or you don't have anybody aligned? I always forget this.
You have somebody aligned.
Okay, derangement is somebody. So you want to avoid a derangement. You want to avoid a reshuffling where the same person gets sent to the same thing twice. So the next time I'm doing it, maybe I now connect him here, I connect her there, I connect him here, I connect this one there again, and that was a waste for me. And that's not happening. That's not helping at all. So this is one of the great applications of derangement theory. It's analyzing these random graph networks and talking about how well connected they are, how quickly information can propagate. The other one, which I'm not going to go into too much time here, is from prime number theory. So p and p plus 2, if they're both prime, we call them twin primes. And it is conjectured that there are infinitely many twin primes. We are getting closer to proving this. There was a remarkable breakthrough in the past 2 years where we now know that there are infinitely many primes that differ by at most, I think it was originally 70 million, and now it's been whittled down to on the order of 1,000. So we're getting closer to being able to prove this. One of the things that people studied was the sum of 1 over p, where p is a twin prime. If this sum were infinite, what would you know about the twin primes? If this sum was infinite, what would you know? There have to be infinitely many twin primes if this sum is infinite. A finite sum of finite numbers will be finite. Sadly, this sum is finite. Mathematicians were able to analyze the sum using inclusion-exclusion, and they were able to get really good upper and lower bounds that converge, and they can approximate the value of this sum. How many of you have heard of the Pentium bug? The Pentium bug was actually discovered by people doing this calculation, by Nicely. He didn't get the same result on his Pentium as people got on the 486, the previous generation of computers. Intel knew that their processor had issues with divisions, but the issues were small. It was like one mistake every billion or trillion divisions in like the 9th decimal place. Who the hell is going to be doing that many divisions to that much accuracy? It ended up being hundreds of millions of dollars, I think, in losses to Intel, just for their reputation. They had just started launching a whole line of commercials. The processor is the most important part of your computer. And their competitors agreed with them and said, yes, we agree, the processor is the most important part. Our processors can divide correctly. And it was a huge marketing snafu for Intel. But this was a nice application of inclusion-exclusion, is finding out what these sums should be in number theory. These become really good ways of testing things. All right, so what I want to do is I want to talk a little bit now about the theory. So we have sets A1, A2, ... AN. These are events. And one of the things you should have realized as we were going through a lot of the calculations with poker hands and perfect deals is that these problems are very simple in practice. Or better yet, maybe they're very simple in theory, but if it's time to actually write down the algebra, they become very painful quickly. It's easy to make a counting mistake. It's easy to double count. A lot of times the double counting might not really matter. When we were talking about perfect deals, the number of hands where only one person has a perfect deal, all cards in one suit, versus the number of hands where 2 or 3 or 4 people all have one suited hands, there's not that much difference. It's so unlikely to have 2, 3, or 4 people one suited that it's essentially the same probability as just having one person one suited. So if you make a mistake, it's going to be in like the 9th, 10th decimal place. People are not going to notice. Okay? From a theoretical point of view, however, there is a difference. There is a mistake. Inclusion-exclusion is to help you calculate the probabilities of certain events easily. And so what we want to do is we want to have simple events. Bad phrases, so these are our events, and they're simple. So easy, what happens at a place, and hard is what happens somewhere. So for example, we have 1 in the right spot in our permutation. So what this means is that when we reorder things, when we take the numbers 1 through n and we shuffle them up and we reorder them, 1 returns to the same spot. That's an easy event to calculate. In fact, does it have to be 1? Could we have done the number 2? Does it make any difference? Are they the same event? Yeah. So more generally, we have the number k in the right spot. What's the probability? So we'll call that event AK. So if k is in the right spot, we have n boxes. K has to be in the right spot. How many choices do we have for the first box? Not n, because remember, k has to be in the right spot. So let's pretend k is right here. So we have n minus 1's choices here. How many choices here? N minus 2. All the way down to 1 choice for the last. And there's 1 choice in the kth spot because we have to put k there. So how many ways can we permute the numbers 1 through n so that k is kept in the right spot? Just there's n minus 1 factorial choices. But how many permutations are there? How many ways can I shuffle the numbers 1 through n? N factorial. Well, this division is not that bad. N minus 1 factorial divided by n factorial is just 1 over n. Kind of what you would expect. The probability, if I have n numbers, that k is in the right spot is 1 over n. It has an equal chance of being in any spot. There's n possible spots, so the probability comes back to where it starts is just 1 over n. This is not a hard calculation to do. The hard calculation to do is not that k is in the right spot, but at least 1 number is in the right spot. This is much harder because now maybe 1 is in the right spot and 5 is in the right spot. Or maybe 1, 5, and 8 are in the right spot. And so these events, these pure events, are very easy to do. The harder events are the at least 1. The idea of inclusion-exclusion, if I have to give you like the 1-sentence summary, the Cliff Notes version, is convert hard events to simple events, but have a lot of simple events to calculate and have a lot of combinatorics to build it together. Frequently in applications, you will have a lot of events that have the same probability of happening. And that'll make the formulas a lot easier. So for instance, the probability that 1 is in the right spot is the same as the probability that 2 is in the right spot, is the same as the probability that 3 is in the right spot. Is they're all the same. And so because of that, it makes the calculation a lot easier. All right, so now the first thing we did, I had stopped following already. All right, so the first thing we did was we calculated the probability that 1 was in the right spot. The next type of event we could do is maybe event Aij is I not equal to j both in the right spot. What would that probability be? The probability that I and j both return to the correct spot. So if we draw all the boxes again, we have one choice in the ith spot. We have one choice in the jth spot. And again, it's possible that maybe I is the first, maybe j is before I. I'm just trying to give you a rough flavor. How many choices do I have here? N minus 2. Right. So that would be n minus 2, n minus 1, all the way down to 1. So there's n minus 2 factorial possibilities. Right? I've got to have two things in the right spot, and that leaves me n minus 2 other numbers to just mix around. I have n factorial arrangements, so I divide by n factorial, and so I'm left with 1 over n minus 1. If I wanted the probability that 3 things are fixed, it would be very similar. Okay? So the idea is these events are not that bad to calculate. The harder ones to calculate are the following. So I'll phrase them as questions. So here's two different events. The probability of the union, the probability of the intersection. Which one is easy, which one is hard? The intersection is easy. So this means that 1 is in the right spot, and 2 is in the right spot, and 3 is in the right spot, and 4 is in the right spot, and n is in the right spot. When you read them out loud, I often find that if you read the events, it's not so bad. What is the arc sine of the sine of x? Or what is the sine of the angle? What are the answers for both of these questions? X. If you just read what's going on, it explains what's going on. I want to take the arc sine of the quantity whose sine is x. All right, so over here, I have the probability of the intersections. This means everything is in the right spot. It's just 1 over n factorial. This is the easy one. What does this mean over here? In words, what event is this?
So is it just A is in the right spot? I mean, 1 is in the right spot, or 2?
Yes. So probability at least 1 is unchanged. So that's one way to phrase what's going on, that at least one thing hasn't been moved. And that's what makes it so much harder. Well, intersections versus unions, okay? We want to try to figure out what's going on with the unions. So this is where we need to go back to our set theory and talk about unions of events. Okay? The idea is we want to expand this probability in terms of the probabilities of simpler events. We like intersections. What does event A1 intersect A2? What will that event be?
The probability of both.
Nope. I'm saying the event A1 intersect event A2. So 1 is in the right place and 2 is in the right place. In our notation, what would this be? A1, 2. So the whole idea here is that we want to replace unions with intersections. So if you think back to the Venn diagram and draw the picture, and I encourage you to do this at home, we want to try to replace this union with lots and lots of intersections. Why? We know how to do intersections well. So one of my favorite quotes, I think I've mentioned this, is if all you have is a hammer, pretty soon every problem looks like a nail. We can calculate intersections. Event A1 intersect A2 means 1 is in the right place, 2 is in the right place. We calculate that probability very easily.
Why can't you just do 1 minus the probability that none in the right place? Isn't that what you told us to do like class periods ago, or like if you have
Okay, so for a lot of things, so what does it mean for nothing to be in the right place?
do shuffling randomly?
Right, but that's much harder to write down. And so for this one, I don't see a nice way to write down the event that nothing is in the right spot. And that's the difficulty. So here, every time I have an intersection, if I have A1 intersect A4 intersect A8, that will just be the event A1, 4, 8. And we can calculate all those probabilities readily. And so what we're going to do now is we're going to look at a set theoretic expression for what's going on and try to look at a good way of decomposing things. So we'll start off with the union. We have A1 union AN. I'm going to put absolute values. So when I'm putting absolute values here, what does that denote? The size of the set. Sometimes people put a pound sign, but in the Twitter era, I'll go back and I'll just use the absolute values, okay? This is counting how many elements are in this set. I want to be very careful. So I claim it's the sum of the elements in AI. So I goes from 1 to n, minus the sum 1 less than or equal to I, strictly less than j, less than or equal to n, of the number of elements in Aij, plus the sum 1 less than or equal to I, less than j, less than k, less than or equal to n, of Aijk, minus dot dot dot. And what you can begin to see is this notation sucks, right? If I wanted to do a general sum, I've got I, j, k, l. It's starting to get confusing. If you go back to calculus, they often use I, j, and k in multivariable calculus for the x, y, and z directions. And then this notation is very bad if you want to generalize to n-dimensional space. And that's why you start using things like E1, E2, E3 rather than I, j, k. So in terms of notation like this, in terms of just writing on what's going on the board, as long as I'm willing to go dot, 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 this is not a bad way to go. But maybe I should do I1, I1, I2, I1, I2, I3. And then it's much clearer how to keep writing everything down. So the question is, why is this true? So what we're doing is we're doing a lot of double counting, but we're being very careful. So what I want to do is for each element x, I want to keep track of how often is it on the left-hand side, how often is it on the right-hand side. I'll only do a little bit, the rest I'll leave the details in the book. So let's go through the different cases. I have n sets, and I want to ask what happens to each element x. So what are the possibilities? X is in nothing, x is in just 1, x is in just 2, x is in just 3, and we go through all the different possibilities. So let's start off and assume that x is in nothing. So I'll call this case 0. X is not in A1 through AN. How many times is x counted on the left? None. How many times is it counted on the right? None. So you get contributes 0 on both sides. Life is good. Now let's assume x is in just one set. Case 1. X is in A1 and nothing else. Is there anything special about A1? No. The same thing would have been if x was just in A2 or just in A3. Let's go back now. So x is just in A1. How often is it contributing on the left-hand side? How often on the right-hand side? It's only in the sum of A1 over here. It's in nothing else. So contributes 1 on both sides. All right, now things start to get a little bit more interesting. So let's do now case 2. X is in A1, x is in A2, and nothing else. So now in this case, we now have x is in exactly two things. So on the left-hand side, how much does it contribute? What does it contribute? It contributes once. Because once you're in A1, doesn't matter that you're also in A2, you're in the union. In fact, as soon as we know it's in one of the sets, we know it's always going to contribute 1 on the left-hand side. Let's go on the right-hand side. How many times is it in these sums? 2. 2 in the first one. How many times is it in the next one? Once. So on right-hand side, contributes 2 minus 1, which is 1. Now, writing the algebra like this, it's not immediately clear what's going on. So what I want to do is I want to look at a special case. I don't want to prove the inclusion-exclusion formula in general. I want to do a special case when all the sets have the same cardinality at the same level. So I'm going to assume all sets with the same number of indices have the same size. You don't need to do this, but in the interest of exposition, I'm going to just make this assumption just to try to make things a little bit cleaner. So now I would have A1 union AN. So this is going to be the number of elements in the whole thing is equal to. Now let's look very carefully at what's going on over here. We've got the sum of the AIs. How many elements, how many sets are there? How many sets are there? A1, A2, A3, AN. How many sets? N. So the left-hand side is just N times A1. We'll see in a moment that this is not the best way to write this. The next one, we have a sum over I less than j, and they go from 1 to n. So how many pairs are there, I, j, where I is less than j, and they're between 1 and n? N choose 2. I'm choosing 2 elements from 1 to n, and I can't choose the same thing twice. Well, if I'm going to call that next one n choose 2, A1, 2, I shouldn't call this n. I should call this n choose 1. The next level, I have to choose 3 indices, I, j, and k, that are not equal from 1 to n. How many ways can I choose 3 indices from 1 to n? N choose 3. And because they all have the same size, it gives me this beautiful simplification. And now when you look and see what's going on, if I have something in various sets, I'm going to be getting the binomial theorem. And that's going to explain where all the algebra comes from. All right, so the rest of the details are in the book. I'm going to stop here. I'll let you look at the book for the rest of the calculation. And then there's a really nice determination of what is the probability of a derangement. So what's the probability if you randomly shuffle that you get at least one element returning to where you started? Anybody remember the answer? We're going to see this answer again and again and again this semester.
It's like around a third.
It's around a third. So it's either 1 over e or 1 minus 1 over e. I forget which way it is. But the answer very nicely involves the reciprocal of e. There's a very high probability that if you just randomly shuffle, something returns to where it started. And it turns out there's a lot of applications of this. We will see an application of this later in the semester. You can either looking at it as how should you determine your spouse or how you should determine whom you should hire. Depending on your point of view, there's a really nice application to the fact that this has a high probability that a certain method works much better than you might expect. So this idea of applications of derangements are very useful. The first time I taught this class, this is called the marriage problem, one of my students promised me that he would use this to determine whom he marries. I will just say that I taught that class many years ago and he is still unmarried. So there may be some issues in actually applying this stuff. I will try to get an update as to how things are going with him. Okay. So this finishes inclusion-exclusion. Again, there's more stuff that you can look in the book. The last thing I want to do, as long as we are doing some of the basic combinatorics here, and I want to leave a little bit of time for induction, is multinomial coefficients. So we're not going to do too much with multinomial coefficients, but it's worth knowing them. If I give you a beautiful state like Maine, right? Why is Maine a nice state? Iowa.
I just said that because he was from Maine, so he went like this. Sorry, I had to.
All right, Iowa. Is Iowa acceptable? I would say even I can spell Iowa correctly. Massachusetts, I've lived here most of my life. I would have trouble spelling Massachusetts. But what's so nice about Iowa is you don't have any repeated letters. How many rearrangements can we make where we use all 4 letters? We can form 4 factorial distinct 4 words. And I believe none of them will be inappropriate words. Right? Another good thing about Iowa. If I give you Mississippi, okay, 11 letters, and I want to look at how many ways can I rearrange the letters. A lot of arrangements are actually going to be indistinguishable from each other. And so the question becomes, how many ways can I rearrange the letters of Mississippi and get distinct words? One of the great ways to attack a problem like this is to add order, to add structure, and then remove it. What I'm going to do is I'm going to put a label on all the S's. S1, S2, S3, S4. I'll put a label on the I's. I1, I2, I3, I4. I'll put labels on the P's, P1 and P2. And because I am just going overboard right now, I've just gotten caught up in the moment, I'm going to put a label on the M. It's actually useful to do this. It's equivalent to multiplying by 1. I now have distinct letters, right? I'm considering S1 different from S2. How many 11-letter words do I have? 11 factorial. But if you look at it, in the 11 factorial, there are going to be 4 slots that are filled by the S's. How many ways can I shuffle the 4 S's among those 4 spots? 4 factorial. And all those shufflings will be indistinguishable. So I have to divide this by 4 factorial. I can also shuffle the 4 I's. How many ways can I shuffle the 4 I's among those 4 slots? 4 factorial. How many ways can I shuffle the 2 P's? How many ways can I shuffle the 1 M? And so the reason I want to put the 1 factorial here is now the numbers in the denominator add up to the numbers in the numerator. So this is called a multinomial coefficient. We'll write it as 11, 4, 4, 2, 1. So multinomial coefficient. Okay, and there's a lot of stuff you can read about the multinomial coefficients. What do you think would be a very special case of a multinomial coefficient? Binomial coefficient, right? There should be good reasons for names like this, right? It's called multinomial. It's generalizing the binomial coefficient. You can get a lot of properties of the multinomial coefficients by expanding. So the binomial theorem this is very important. X plus y to the n is the sum. K goes from 0 to n choose k. X to the k, y to the n minus k. And one way to view this is when I expand this out, I have n factors of x plus y. For each factor, I either choose an x or I choose a y. So if I want to get a term x to the k, y to the n minus k, I have to choose the x k times. If I have n factors, how many ways can I choose k of the n factors to give me the x? So how many ways can I choose k of the n factors to give me the x? Just someone say it. And choose k. And now, technically, I actually have n minus k factors remaining, and I need to choose all of them to be y. I really have a 1 floating around. Most people are not as gung-ho about writing 1 as I am. And they would just simplify the formula, and they would not bother to put this in. But this is really what's going on. It gives you an idea, though, of what you would get for the trinomials, x plus y plus z to the n. Well, one way you could view this is you could view it as x plus y plus z to the n. Basically, do it with grouping. We know the binomial theorem. We expand this with the binomial theorem, and then we expand y plus z with the binomial theorem. Or we could try to tell a story. And the story would be, I need to get terms. It's going to be of the form x to the a, y to the b, z to the c, 0 less than equal to a, b, c less than equal to n, a plus b plus c equals n. And I'll let you ponder what probably goes in over here. In the multinomial formula, I will let you try to figure out what probably goes over here. Okay? All right. So we have 5 minutes left. You should hopefully have seen proofs by induction in linear algebra or multivariable calculus, but just in case, I want to quickly go over proofs by induction. There's a lot more about this in the appendix. So the way it works is the following. You have some statement Pn. You want to prove for all n. Well, you could say, let's try to prove, and there's debate depending on the problem as to whether or not you start with n equals 0 or n equals 1. Let's proof statement P0, proof statement P1, proof statement P2, proof statement P3. You prove the first billion of them. You may begin to get confident that the statement is true, but it's not a proof. We want a formal way to prove all of these statements simultaneously. And you do the following. Step 1 is prove P0 is true. And this is called the base case. And then step 2 is prove if Pn is true, then Pn plus 1 is true. And this is called the inductive step. And if you can prove these two things, then Pn is true for all n. So this is wonderful. If you can just prove it in the beginning and then show whenever it's true for Pn, it's true for Pn plus 1, then you can just march down the line. And one simple way to see this is to draw like a little flow chart. So we have P0 is true. Now I know that whenever Pn is true, Pn plus 1 is true. What would be a good choice of n? 0. So we know P0 implies P1 is true. Well, if P0 implies P1 and P0 is true, what can we conclude? P1. So now we know P1 is true. Now we go back and we know whenever Pn is true, Pn plus 1 is true. What should we choose for n? 1. And we can see how we just march down. P1 implies P2 is a true statement. Therefore, what do we conclude?
It's true for all.
Well, technically, what do we conclude here? P2 is true. And now you just continue marching down the line. And so there's lots of different standard proofs by induction. And so there's a couple of them in the appendix to the book. I think it's Appendix A. If you haven't seen proofs by induction before, I strongly urge you to go to the appendix, look at some of the stuff there. I will do the standard boring one that I think is required to do. So Pn, no, I can't do it. It's too boring. 1 plus 3 plus 5 plus 2n minus 1 equals n squared. That's more fun, right? The sum of the first so many odd numbers is a perfect square. There's lots of proofs of this. There's the geometric proof. Okay, does 1 equal 1 squared? Now I have to add 3 dots. 1, 2, 3. I have a 2 by 2 square. I now add 5 dots. I now add 7 dots. 1, 2, 3, 4, 5. So this is a geometric way of proving it. I know I'm supposed to show that the sum of the first n integers is n plus 1 over 2. I just can't do it. I've taught this class too many times. I need to do something different. All right. How would we prove this? Well, let's check the statement P1. So does 1 equal 1 squared? Yes. So the basis case is true. Now we assume Pn. So we're going to assume 1 plus 3 plus 2n minus 1 squared equals n squared is true.
Where's the square coming from?
From typos. No problem. So we're going to assume Pn is true. We want to show Pn plus 1 is true. What's nice is most of these proofs are follow your nose. Let's look at what Pn plus 1 is. So let's look at 1 plus 3 plus 2n minus 1 plus 2n plus 1 minus 1. That's the expression we have to look at. All right. I can simplify this a little bit. 1 plus 3 plus 2n minus 1 plus 2n plus 2, so it becomes 2n plus 1. Now, whenever you're doing proof by induction, you're assuming Pn is true and then trying to show Pn plus 1 is true. So somehow you've got to find Pn lurking in the expression you're attacking for Pn plus 1. Does anybody see where the expression for Pn lives? Yeah, it's just over here. That's exactly the quantity that Pn is telling us about. By assumption, this equals n squared. So n squared plus 2n plus 1. And now that's just n plus 1 squared, and that's the proof. So when you're proving things by induction, the goal is to try to recognize on the left-hand side what you're assuming. This does not mean that we have proven that Pn is true at this point. We are just assuming Pn is true. We have 1.5 minutes. This might be enough time. I need a volunteer who has an ID on them. Quickly, quickly, quickly. Somebody with an ID who can take it out really fast. All right. Everybody is named Lawrence. All right.